We are going to learn about space and time complexity in Python in this lesson. Time complexity in Python refers to the measure of the amount of time or the number of operations required by an algorithm or a program to run as the input size increases. It helps in understanding how the running time of an algorithm grows with the size of the input. Time complexity is typically expressed using BigONotation. Now, here are some commonly encountered time complexities in Python. Big O1, constant time complexity. An algorithm with constant time complexity takes a constant amount of time to execute, regardless of the input size. It is the most efficient time complexity. Let us take an example. So we have a function named print first element that takes a list as an input parameter. The purpose of this function is to print the first element of the input list. For this, it accesses the element at index 0 of the list and then prints it using the print function. Let us take two inputs for this function with different sizes to check the time complexity for both the inputs. The first input is 1, 2, 3, 4, whereas when we take the second input as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is comparatively a larger input, then this takes the same amount of time to execute the program. Now let's talk about the time complexity. In this particular code snippet, regardless of the size of the input list, the time it takes to execute the function remains constant. This is because accessing the first element of the list does not depend on the size of the list. It directly accesses the first element without any iteration or traversal through the entire list. Hence, the time complexity of this code remains constant, or O1, which means the execution time does not increase as the input size grows. It is an efficient and fast operation. This concept of constant time complexity is useful when we have specific operations that can be performed in a fixed number of steps, regardless of the input size. Now, let us talk about the programs that have linear time complexity. Let us take an example of a program which has a linear time complexity. In this function, there is a for loop that iterates over each item in the list. The loop variable item takes on the value of each element in the list one at a time. Inside the loop, the code prints the value of each item using the print function. So when you call this function and pass a list to it, it will iterate through each item in the list and print it. Let us take some examples and check the time taken by this function. In the first example, when we are taking a list with 4 elements, 1, 2, 3, 4 as input, whereas when we take a list with 10 elements, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 as input, the time complexity of this code is linear, denoted as big O(n), where n represents the size of the input list. This means that as the size of the list increases, the time it takes to execute the code will increase proportionally. For example, if the list has 4 elements, the code will iterate 4 times. If the list has 10 elements, the code will iterate 10 times. Understanding time complexity helps us evaluate the efficiency of algorithms and how they scale with larger input sizes. In this case, the time complexity indicates that the execution time of the code grows linearly with the size of the input list. Now let's talk about the programs that have quadratic time complexity. Let's take an example of a program which has a quadratic time complexity. So here we have a function named print pairs that takes a list as input. Inside the function, there are two nested for loops. The outer loop iterates over each element I in the list. And the inner loop also iterates over each element j in the list. For each pair of elements ij, the code prints them using the print function. So what does this code do? It essentially prints all possible pairs of elements from the given list. Now let's take two different examples. In the first example, let us take the input as the list having two elements 1, 2. And in the second example, let's take the input as the list having 4 elements 1, 2, 3, 4. So you can clearly notice that the difference between the runtime of the programs with different inputs is huge because of the size of the input. Now this implies that the time complexity increases quadratically with the size of the input list. For a list of length n, the code will perform n iterations for the outer loop and n iterations for the inner loop, resulting in n into n, that is n squared iterations in total. So, as the input list grows larger, the time taken by the code to execute will increase significantly. Well, I hope that you have thoroughly understood about time complexity of programs. It's now time for us to learn about the space complexity of a program in Python programming language. Space complexity in Python refers to the measure of the amount of memory or space required by an algorithm or a program to run as the input size increases. It helps in understanding how the memory usage of an algorithm grows with the size of the input. Space complexity is expressed in terms of the additional space required by the algorithm, excluding the input space. So here are some commonly encountered space complexities in Python. O1. Constant space complexity. An algorithm with constant space complexity uses a fixed amount of memory regardless of the input size. Let's take an example to understand it better. This code defines a function called sum of two numbers that takes two parameters, a and b. Inside the function, it calculates the sum of a and b and stores the result in a variable called total. Finally, it returns the value of total. The code shows an example of a function that performs a simple addition operation, takes two numbers as inputs, adds them together, and returns the sum. Regarding space complexity, the code has a constant space complexity. This means that the amount of memory used by the code remains the same regardless of the input size. In this case, the space used is minimal, as it only requires memory to store the input parameters, that is a and b, and the total variable. The memory usage does not depend on the size of the input, so it remains constant. Now, if you take a look at the examples, you can see that in both the cases, the output is a single number. So the space complexity is constant in this case. Overall, this code serves as a basic illustration of a function that calculates the sum of two numbers and showcases an example of constant space complexity. Next, we have the linear space complexity. An algorithm with linear space complexity uses memory that grows linearly with the input size. To understand the time complexity of this code, we need to consider the number of iterations the loop goes through. In this case, the loop iterates n times, where n is the input size. So, the time complexity of this code is linear, or ON, meaning that the time required to execute the code increases linearly with the size of the input. In terms of space complexity, the code utilizes additional memory to store the list, which grows with the size of the input n. Therefore, the space complexity is also linear, or ON, which you can also notice in the given example. In the first example, the input is 4. So that program creates a list of 4 elements. But in the second example, when the input is 10, the program creates a list of 10 elements, which means the space consumed by the program increases linearly with the size of the input. Overall, this code creates a list of size n by iterating through a loop and appending values to the list, resulting in linear time and space complexity. Finally, let's talk about the quadratic time complexity. An algorithm with quadratic space complexity uses memory that grows quadratically with the input size. It often occurs with nested data structures or when generating all possible combinations. This code defines a function called generateMatrix that takes a parameter n, which represents the size of the matrix we want to generate. Inside the function, we create a variable called matrix and assign it a value. The value is obtained using a nested list comprehension. Now let us break it down further. This line creates a 2D matrix represented as a list of lists with dimensions n by n. Each element of the matrix is initialized to 0. This expression creates a list of n zeros. The outer for in range n loop is used to repeat this process n times, creating n sublists, each containing n zeros. As a result, we get a square matrix with all elements initialized to 0. Finally, the matrix is returned from the function as the output. To summarize, the generateMatrix function creates a square matrix of size n by n, with all elements initialized to 0. The size of the matrix and the space required to store it increases quadratically with the input size n, as we are creating n lists, each with n elements. Well, I hope that you have understood about the amazing concepts of time and space complexity. These concepts are very, very important and useful to a programmer and a data scientist. So take note of them.